Okay. I'm just going to go briefly over basic circuits and then let's do transients in AC and DC. That is problem set 2. And then Brian will go over body plots again. If you have any questions regarding op amps, let's do that at last. Okay, just a quick recap about the formula sheet. If you have any questions regarding formula sheet, let us know. And yes, the basics of circuits. You don't have diodes in the exam, so we're not going to go over diodes. And voltage. What is voltage? How do you measure voltage? It's the difference between the potential between 2 points, right? If it's VA and if this is VB, and let's say that this resistor has a voltage of VR, your voltage VR is equal to VA minus VB, assuming this is VA is greater than VB. Correct. And how does the current flow here? It's going to flow from a higher potential to a lower potential, right? And this is our current flowing in this resistor IR. And next, we have resistor loss. What does Ohm's law say? Let's see that the resistances are, your VR is equal to IR times R, right? This is our resistor voltage and the resistor current. We just have IR equal to VR by R. And also make sure to follow the current direction while you're making your Ohm's law. If you have your current in this direction, let's call this VC, VE, and VF. This is your R2 and this is your R1. You have a current flowing like this, and we have a current flowing like this. So how do we write the equations using this information? If you're assuming your current to be flowing from node VE to VC, you are expected to put that node first in your voltage equation, that is VE minus VC by R1 is equal to I1, right? And for I2, we are assuming that it's flowing from VC to VF. So we have VC minus VF by R2. You cannot consider your current to be flowing in this direction. Let's call it I2 dash. It is not equal to VC minus VF by R2. Your I2 dash is now equal to VF minus VC by R2, correct? if you assume it to be like this, that is going to give you an incorrect answer, and will that will result in cutoff of points. So make sure that your current direction and your Ohm's law is in sync. And next, capacitor loss. Could one of you unmute and tell me what is the formulae for IC of t and VC of t? Hey, Brian, what is the value of VC of t?
Oh, yeah, it's
Oh,
your.
I said Brian, not Ryan.
Oh, Brian. Oh, I heard me. I'm sorry.
Hold on, what was the question? I missed it. I was sorry.
Yeah. What is VC of t equal to?
Assuming Ohm's law, wouldn't it just be IR for voltage?
The capacitor voltage.
Oh, the capacitor voltage.
Mm.
I don't remember. Make sure to add that on the formula sheet.
Will that be IZ?
Yeah. Remember this? Your IC of t is equal to C dV by dt. So what is your VC? Oh, your VC is integral C IC of t dt, correct? Is that right?
Yeah, that's right.
Hmm. Okay, now, who wants to tell me what's KVL and what's KCL? Come on, guys. KVL, KCL. Let me give you a circuit example.
So KVL is a
Hey,
voltage.
hey, no, no, no. You've been answering a lot. No.
Okay.
Yes. Let's give others a chance.
KCL is when all of the currents within the circuit all sum up to equal 0. And then KVL is when all of the voltages in the current sum up to equal 0.
Yep. And how do we apply KCL in this case? Okay, someone else answer now. I'm going to call up names. Let me ask. Hey, Ryan English, are you here?
Yes, I am.
Yeah, tell me, how do we apply KCL in this for this circuit?
You you have nodes A and you have nodes B. So for node A, you do the currents going into or out of the node. So you'd have one from V1, you'd have one out there, and then you have one out there. Yeah.
Yeah, perfect. Okay, you seem very prepared for the exam. Pretty good. Okay, now someone tell me, how do we apply KVL here? Rico, come on, let's go. Answer me.
So in order to use KVL, so there's two loops in the system, and we can set both loops equal to 0. voltage. So we can find the overall voltage by setting two different like closed loop systems equal to 0.
And what would one of the loop be?
So we could do, yeah, so it would be like our yeah, so it'd be like for the one on the right, we can call that like I1. So I1 times, or sorry, the one on the left, it would be like V in minus R1 times I1 is equal to 0.
Or 1 times
I1,
minus I2?
that would yeah, minus I2. Yeah.
And this is equal to
Because
0?
and then for the one, or I guess it depends on the orientation of the resistor, like however we tell it that the current is going towards.
Yeah.
We just have to keep
Okay.
it consistent with the other loop.
Okay, now can somebody else tell me what the second equation would be for KVL?
I actually have a quick question. So I would have assumed that Vn would be negative because the arrow is going into the negative side of the voltage source. So it doesn't matter which one we do, negative or positive, as long as one's either or.
You mean the current is going this way,
Yeah.
but it's coming out of the positive end, right?
Oh, so it's by where it comes out of, not where it goes in.
If it was connected as negative and then positive, and this was your loop direction, let's call it VA. In your equation, it would now be negative VA.
So the voltage sources will always be positive, you're saying?
It depends on the sign. If it's negative that your voltage, that your current is coming out of, then it's going to be negative VA. If it's positive note that your current is coming out of, then it's going to be a positive.
I see. Okay. If I did the first example as a negative Vn and plus R1 times I1 minus I2, would that give me still the same answer?
Yeah, if you had opposite signs for this one and this part, I think it would give you the same.
Okay. Thank you.
Yeah, as long as you're consistent, you should be fine.
With your signs.
Yeah.
Okay, now who's going to give me the equation for the second loop? Braden?
Hello. I think it would be R2 times I2 minus I2 times R1. Oh yeah, let's take that back. Let's go yeah, R2 times I2 minus R3 times I2
Minus?
plus.
Yes, it's a plus. And
And then
next,
the last thing is going to be let's do R1 parentheses
hmm,
R
hmm,
or I2 minus I1.
yes, that is it.
Sweet.
Yeah, that is our KVL. Pretty good. Is everybody clear with KVL and KCL? Are there any questions? These are important. So, yes, please review KVL and KCL. Okay. And next, we have our DC source and AC source. When you have a DC source, it's going to be represented with a positive sign and a negative sign. And you usually use capital letters to denote your DC source, and your AC source is represented using a sine wave, and it's usually denoted in small letters with a T. Okay. And next, we have Laplace transforms. Make sure to include this in your formula sheet. Okay. And next, impedance. Let's look at, yes, I grabbed these from one of the lecture slides and I put them here. Please do review them. Yes. How do we get our impedance? What is impedance? What is impedance, guys? Let me ask Carolina. Carolina Avila, do you want to answer? Do you know what answer? Okay. Beauty, how about you? Do you want to answer?
Isn't impedance it's similar to resistance, right?
Yes, your impedance is similar to resistance. And let's say I had C1 and C2. I had two resistors. Oh, Carolina. Yes, that is perfect. I had two capacitors connected in parallel. Could one of you tell me what is the impedance corresponding to this capacitor combination? And let me also put this. Hey, Tyler, do you want to answer this? And who else? Ryan Spencer. You don't have to unmute. You can just type in your answer in the chat as well, if you're not comfortable speaking.
What are you asking?
I'm asking what is the impedance corresponding to this circuit and the circuit?
Uh, I know you combine them and do like an equivalent capacitance,
Yeah.
but I don't know what you do beyond that.
What is the equivalent capacitance for this circuit?
I want to say C1 plus C2 for the top one.
That is correct.
Okay, so the bottom one is just 1 over C1 plus 1 over C2.
Yep. So what is your ZC for each of these?
Would you just plug the equivalent into the C value for the equation?
Yeah. Right. And for this equation, we have 1 by 2 pi f times 1 by C1 plus 1 by C2. C1 plus C2 times, C1, C2, C plus C2. Correct?
Amelia, I have a question.
Yeah.
For the capacitance in series, that 1 over C1 plus 1 over C2, isn't that all to the -1 as if it was a resistor in parallel?
What?
Yeah, it should be, it's the reciprocals. Yes, it's 1 over, yeah, there you go.
Yeah. So it is
Can I get some
C1
extra credit?
C2 by C1 plus C2. This one would be 1 by C1 plus C2 by C1 times C2. And what would this be now? Oh. Would the impedance be, guys?
It would be C1 plus C2 over 2 pi f C1 times C2.
Yes. That is it. That is our impedance. And also remember that at high frequencies, your capacitor behaves like a short circuit. And that means there is no current flowing. And at low frequencies, your capacitor behaves like an open circuit, right? Let me give you an example for a short circuit. At very high frequencies, this would be your equivalent circuit. Okay, there is no potential difference at this end and this end, and hence there is no current flow. Oh no, there is current flow. There's only current flow. There is no voltage difference. Your voltage, let's call it V naught of t, that's going to be 0. And at low frequencies, your circuit is going to be an open circuit. You would have a voltage difference, but there is no current flow. Okay? Is that clear?
Are we gonna have problems with inductors as well, only capacitors? Are we going to have problems with inductors as well, or only capacitors and resistors?
Did you do inductors in the class?
I just want to make sure.
If you did not do it in the class, obviously it's not going to be in the exam. Okay, this is just a slide summarizing your alternating current input source and your diacurrent input source. Okay. Just go through this again. And now let's go to problem sets. Do you have any specific questions that you want me to solve from problem set 1? I haven't chosen any questions, so if you do not have any questions, I'm just going to skip and go to problem set 2. Is that cool?
Yeah, can we do problem set 2, please?
Okay.
Are capacitor voltage and current graphs going to be on the exam?
Capacitor voltage and current graphs, yes.
Could we go over those, please?
Oh, yes. VC of t plots. Let's say the time constant corresponding to this is RC. And how many time constants does it take for the capacitor to fully charge?
Was it, oh,
Yes, 5. You're correct, Ryan. So it takes 5 time constants time for the capacitor to fully charge. And we assume that in one time constant, your capacitor reaches 63% of its fully charged capacity. Okay. And in 5 time constants, it is at almost 100%. Okay. In ideal conditions. And the maximum voltage that it can reach is the input voltage, right? And what is our output voltage or the voltage across the capacitor given as for this specific circuit? How do we solve it? What do we equate to find the relation between V in of t and Vc of t? If you know this, you get like 100 points in the exam tomorrow. Yeah.
Wait, I got you.
Yeah, tell me.
VC of t equals the integral of I over c dt.
I mean, yeah, that is the equation, but I'm asking you for the equation that relates your Vn of t and Vc of t.
Do we do V in of t? Oh, sorry. VC of t equals V in of t times 1 minus e to the power of negative t by RC?
You mean this equation?
Yes.
Yes, that is correct. Where did you get it from?
Well, you get it because, well, okay. You get it using the KVL, right?
Mm-hmm. KVL, yes, or KCL.
KVL, pretty sure.
Okay.
And then you also use Ohm's law as well.
Mm-hmm.
So
And do we convert our equation or our circuit into another domain?
yes, you have
Mm-hmm.
to
How do we do that?
you have to do, I'm pretty sure you have to use impedance, correct?
Okay, wait. Let me open a. Wait, hold on. Hold on. Yes. Do you all see my whiteboard?
Yeah.
Okay. No. I cannot see the chat anymore, so if you have any questions, you would have to unmute and speak or join me. Okay, now. So what do we first do? Do we convert this into frequency domain using Laplace? Yes or no?
Yeah.
You find the impedance first?
We find what?
The the z of r and c.
Yeah. Am I correct?
Yeah, you are.
Okay. So we have Vn of s, zr, zc, plus minus vc of s. Yes. Please do note that I'm also converting my output and input voltage into Laplace domain. Okay. And now, what do we do now? Do we apply KVL or KCL?
KVL.
KVL.
How do we apply that? We do Vn of s minus Vc of s by Zr is equal to Vc of s by Zc, right? because this is a very simple equation, I'm just equating the current going in this resistor and the current going in this capacitor, okay? IR and IC, and IR is equal to IC, right? Is that correct? Okay.
Yeah.
Now, simplifying this further, I'm trying to get an equation for VC of S in terms of V in of S and ZR and ZC. So I'm going to get all the VC terms to one side. And next, I'm going to is this okay? Oh my God, this is not working. Okay, it's working. Oh, ZC times ZR. This is not working. Oh, it's working. I simplified it further and got to this term. Is that clear? And because we have a ZR in both of the denominators, I'm just eliminating it. And now we have VC of S times ZC. Okay. ZC plus ZR. I'm just flipping the side. VC of S is equal to Vn of S times ZC by ZC plus ZR. Is that right? Is that correct? Are you following? And now VC of S is equal to, and I'm just substituting the values for ZC into my equation. That is 1 by SC by 1 by S plus R. And this would be and now I can cancel this and this because they're both in the denominators, correct? And how did we get oh, why is this freezing? Vn of t times 1 minus e to the power minus t by RC. Oh. Yes. How did we get from here to here? What did we use?
We use the Laplace transforms.
Yeah. What is the equation that we used? Oh my God. Okay. Let's just go with this for now. I will post an explanation for this later and not now. Okay. Yes, we were talking about plotting. So VC of t plot. Assuming that VC of t is the output, and our tau is equal to RC. And this is time, and this is our VC of t. So if you put your t as tau, what are you going to get in this equation? It's going to be 1 minus e to the power minus tau, which is RC by RC, right? What is e to the power minus 1? What is e to the power minus 1?
One over e.
Yeah, 1 over e, but what is the value of 1 over e? It's 0.367 something. So when you subtract 0.367 from 1, okay. This is going to be 0.64 approximately, correct?
Yeah.
And this is also, we can also say that it is 64% of V in, right? This one.
Yeah.
So at 1 tau, your capacitor is charging to 63 or 64% of your input voltage, right?
Yeah.
So let's say this is 100%. That is V in. That is 90%, this is 80, 75, and this is 60. So at 1 tau, it's going to be at 63%, right? And now let's look at VC of t. Vn of t, 1 minus e to the power. So let's go with the t value as 3 tau. What do you think this answer is going to be? Minus 3 RC by RC. What is e to the power minus 3?
Is 0.0498.
Yes, it's going to be 0.049. And when we subtract this from 1, what do we have? What do we have? We have 0.95. And this is 95% of V in, right? So at 3 tau, your capacitor tau tau. This is almost reaching to 95. So it's over here. And by the time it reaches 5 tau, it is fully charged, correct?
Yeah.
This is the plot that we get for charging.
Do you think you can zoom out so I can see all the steps in the graph together?
Is that better?
No, like when you're calculating the plugging in the -3.
Oh,
Yeah, that's fine. Thank you.
and we talked about one other way to determine how this plot looks like, right? That is 1 minus e to the power minus d by RC. So how is your e to the power negative 80 plot? E to the power 80. What is the value when t equals 0?
Doesn't it just swoop all the way down? Like it'll go to the 0 is gonna go to like infinity, and then it swoops down from there. Like as x approaches infinity, it goes closer to 0.
What is the value of this when t is equal to 0?
It's gonna be 1.
Right? And it's going to be a decreasing plot like this.
Yeah.
And now, if we subtract 1 from this, 1 minus e to the power minus at. We can do it step by step. Let's first flip our signal because there is a negative sign. How is it going to look like? It's going to be starting from -1 and it approaches infinity after a while, right? This is our negative e to the power minus at, correct?
Yeah.
And now we are shifting our signal by a value of 1. So how is the signal going to look like now? 1 minus e to the power minus at. We have an amplitude shift of 1. It's going to start from 0 or 1. It's going to start from 0, right? This signal has an amplitude shift of 1. From -1, if you add 1, it's going to end up at 0, correct? And that is why the shape of the plot is like this. And another way to prove the shape of that plot is using this math, where you insert the value of t as tau. You can test it out. Tau, 2 tau, 3 tau, 4 tau, and 5 tau. At 5 tau, what should you be getting? What is the value of VC of t? One minus e to the power minus 5 RC by RC. These get cancelled out. What is e to the power minus 5? It is 0.0068. And when we subtract this 0.0068 from 1, what are we going to get? You're going to have 99, 0.9932, right? And this is approximately equal to 99% of V in, correct? And this is at 5 time constants. And that is what we assumed, or that is what we know. And that is how we plot our signal. At 5 time constants time, your signal almost approaches V in. And what happens during discharge? Your signal is going to gradually decrease with time, right? This is your charging curve, and this is your discharging curve. And that is your capacitor voltage plot. I think this also pretty much sums up problem set 2. Or did you have any specific questions in problem set 2? Okay, Ryan, do you want to go over body plots again?
Yeah, absolutely.
Let's go.
All right. So, could you close the whiteboard?
Yep.
Perfect, thank you. All right, can you see all right? Oh, why did it go back to Zoom? There we go. All right, so for Bodie plots, you're gonna have your transfer function, h of s, which you can also write as h of j omega. And it's gonna be, I'm just gonna use a fairly simple and generic one here, but it's gonna be something along the lines of 1 over 1 plus j omega rc, right? So what we need to find here when we're looking for Bodie plots is magnitude and phase. So our magnitude equation is going to be, the simplest way to do it is going to be the square root of your real component squared plus your imaginary component squared. And for your phase, it's going to be the inverse tangent of your imaginary component over your real component. That's the simplest form of your magnitude and phase equations. Now, how do we actually apply these to our transfer function? Well, we want to find the magnitude, and we're going to look at both the numerator and the denominator. So we're finding our magnitude of our h of j omega is going to be the magnitude of the terms in the numerator divided by the magnitude of the terms in the denominator. In this case, we only have one term in each, right? So in our numerator, we have just 1. There is no imaginary component here. So we're going to have the square root of 1 squared, right? Which simplifies to 1. But in our denominator, we have our real component as 1, and we have our imaginary component as omega rc. So we're going to get the square root of 1 squared plus, drop the j, omega squared, r squared, c squared. Once we have this equation, we can simplify a little bit. So our numerator is just going to be 1. Our denominator, we're going to have 1 squared plus omega squared, r squared, c squared. Now, in order to actually plot it on our Bodie plot, we want to find the gain in decibels, right? So if we just plug in our omega to what we have right now, this would give us our linear gain. In order to convert it to decibels, we do 20 log base 10 of that. So we get 20 log base 10 of 1 over the square root of 1 squared plus omega squared r squared c squared. Now, with our log rules, we can simplify this in two different ways. The first way we can do it, we know our division sign, or our fraction, whenever we have division, we can rewrite that expanded as 2 log terms subtracted. So we can simplify this down to 20 log base 10 of 1 minus 20 log base 10 of our square root of 1 plus omega squared r squared c squared. And then we can simplify this a little bit more because we can bring our square root to the exponent. And then we know with logs, whatever we have in the exponent, we can move into the coefficient out front. So we're going to end up with 20 log base 10 of 1 minus 10 log base 10 of 1 plus omega squared r squared c squared. Right. Now our log base 10 of 1 is going to be 0, right? Because log base 10 of 1 is 0, so that whole term goes to 0. And we're left with just our minus 10 log base 10 of 1 plus omega squared r squared c squared. And this is going to be our gain. Specifically our gain in decibels. So this is going to govern our magnitude plot. So what we can do is we can plug in different values of our omega and solve for our associated gain. So we can sub in if omega is equal to 0, our gain is going to be equal to what? Well, if we substitute omega equal to 0, our whole omega RC term is going to go to 0, right? So we're going to be left with negative 10 log base 10 of 1. And as we said before, log base 10 of 1 is 0, so the whole thing's going to go to 0. So we're going to start from 0 decibels. If our omega is equal to 1 over RC, which would be our cutoff frequency, what's going to happen? Well, if we take a look at our equation, our omega is squared, right? If we substitute in our RC, we're going to get 1 over RC squared, which we can write as 1 over R squared C squared. All right. That's going to make our term, our omega RC term, go to 1, right? Because we're going to have 1 over R squared C squared times R squared C squared. So that's going to go to 1, which means the inside of our log is going to go to 2. What is log base 10 of 2? Let's plug it in the calculator here. Log base 10 of 2 is equal to 0.301, right? We multiply that by our negative 10. That's where our negative 3 decibels come from, right? So our gain at our cutoff frequency is negative 3 decibels. And finally, if we take the limit as omega goes to infinity, what happens? Well, we can just think about it. What happens if we keep plugging in bigger and bigger numbers? The term inside of our log is just going to get larger and larger and larger, right? So if we plug in infinity, the term inside of our log is going to go to infinity. Our log is also going to go to infinity. 10 times infinity is infinity, right? But we have a negative in front, so it's going to go to negative infinity. So as our omega continues to increase, our gain is going to continue to get more and more and more negative, right? So this is going to go to negative infinity. Once we have this, we have everything that we need to graph this, right? Because if we take a magnitude plot, we have omega on our x-axis. We have the magnitude of our, I'll just write gain in decibels on our y. We're going to start from omega equals 0. Let's say, let's draw it first. So let's say this is our cutoff frequency, 1 over RC. We know that our cutoff frequency is going to be minus 3 decibels, right? So let's say this is our minus 3 decibels. And then we know because we have a pole, our graph is going to continue down at minus 20 decibels per decade. Any questions on the gain or on the magnitude plot there? How we derived our gain expression, plugged in our points, and found our graph? Is that all making sense? All right. If you have any questions, shoot them in chat. I'll try to get to them. But let's go ahead and look at our phase. So our phase here, we have the inverse tangent of our imaginary over real. And we're going to do the same thing as before where we're looking at the numerator and the denominator. So we have phase is equal to the inverse tangent of imaginary over real. And the important part to remember with the phase equation is if it's in the numerator, it's going to be positive, and if it's in the denominator, it's going to be negative. But we can apply the same thing. Oh, this should be negative first. So this term, the first term is going to be for the numerator, and the second term is going to be for the denominator. So if we apply this to our equation that we have 1 over 1 plus j omega RC. For our numerator, we have inverse tangent of 0 over 1, right? Because we have no imaginary component in our numerator. We only have a real component. And then we subtract and do our denominator term. So we have minus inverse tangent of omega RC over 1. Because our real component in our denominator is 1, and our imaginary component is omega RC. So we can simplify this equation. Our inverse tangent of 0 is just going to be 0. So this first term is going to go to 0. And we can rewrite this as the negative inverse tangent of omega RC. And now we can apply the same logic that we did before where we just plug in different values of our omega. If omega equals 0, our omega RC term is going to be 0. And we just said the inverse tangent of 0 is 0. So our phase is equal to 0. If omega is equal to 1 over RC, we're going to have the negative inverse tangent of RC over RC, which is equal to the negative inverse tangent of 1, which is equal to negative 45 degrees. Right? And that makes sense because we know that our poles and zeros are going to give us a 45-degree shift at our cutoff frequency, right? And if we take the limit as omega approaches infinity, our phase is going to go to negative 90. This should be 0 degrees. Should make sure I have my units. So once we have these 3 points, we can approximate our phase plot based off of this. We're going to have omega, or our frequency on our x-axis, we're gonna have our phase on our y. This is gonna be 0, -90, and -45. We'll have our cutoff frequency here. And our phase is gonna look something along the lines of this, where this is our cutoff frequency. And as we increase our, I kind of drew that, I'm gonna leave it. It's gonna go to -90, right? I drew that kind of poorly, but you get the gist. It's gonna start at 0, it's gonna curve down through -45 at 1 over RC, and it's gonna go to -90 as omega increases. Right, this 3 points gives us enough to approximate it. If you were doing this in a real engineering situation, you would want to plot more points to get a more accurate curve, but this is good enough for this sake, right? So you just need to remember these magnitude and phase equations and then how to apply them to your transfer function, right? Does that all make sense? Any questions on that? How we feeling? Give me a thumbs up if you're feeling all right on Bodhi plots.
Yes.
All right,
I do also want to mention. Oh yeah.
yeah.
I do also want to mention about DC gain real quick.
Okay.
So, how do you get your DC gain?
Should I ask
So
a quick question before we go to that about
yeah, absolutely.
Ryan's drop? It's something simple, but when you're doing the inverse tan of the imaginary over R,
Mhm.
you just put omega RC. Do you just neglect J because it's already imaginary?
Yeah. Yep, so you just drop your J for
All right,
your
thank you.
imaginary term. Yeah. And it's
That
the
is the
same thing.
equation for your absolute value for a complex number. You do not consider your J. Your absolute value is just square root of real squared plus imaginary squared.
Yeah.
And yes, DC gain. So
So
you get DC gain by making your J omega or S values equal to 0 and whatever that is left. So for example, in this equation, yes, if you substitute your J omega with a 0, your DC gain is just going to be equal to 1, right? Yep. And this is the point where your plot is going to start from the magnitude of 1. What is 20 log 1 base 10? It is 0, right? So when your DC gain is 1, it would not have any effect, but make sure to calculate your DC gain. Your DC gain is effective in all cases, positive and negative, except for when it is 1. Okay? That is all that I wanted to say.
awesome. And I'll give the beginning of a more complex example, just setting up the equation. So let's say our transfer function is some complicated mess. It's like J omega plus 10 times J omega plus 20 over J omega minus 5 times J omega plus 40, right? We can take these same equations, these same generic equations that we talked about, and we can apply them over here as well. So our magnitude is going to be equal to the square root of omega squared plus 10 squared times the square root of omega squared plus 20 squared divided by omega squared minus 5 squared times the square root of omega squared plus 40 squared. Right, so this would be our linear gain equation or magnitude equation, right? And then if you wanted to plot it, you would do 20 log base 10 of that. It would get complicated. It's beyond the scope of the class, right? But just to show you can apply this to multiple terms, right? And the same thing with the phase. You would get the inverse tangent of omega over 10 plus the inverse tangent of omega over 20. So these are our two numerator terms, right? So that's why they're both positive. And then we have minus the inverse tangent of omega over -5 minus the inverse tangent of omega over 40. This would give us our phase, right? And again, we plug in different values and we can plot it. So, how we feeling? Is that all right? Do we feel like we kind of got Bode plots? All right, I'm taking that as a yes. I
Sorry,
got
I
two
have one
thumbs
more
up
quick
early.
question. I
Yeah.
was just writing down. In this complex example, we have the square root of omega squared minus 5 squared.
Mm-hmm.
And
Oh, this should really be
oh,
plus.
it should be plus. Yeah, that's what I was.
Yeah.
That was my question.
Good catch. That should be plus.
And one more thing to add, you would just be adding your DC gain to the equation and the magnitude, just plus whatever gain that you get from this equation. So here the gain is
What would it
oh
be?
-1.
200 over -200. Yeah, so this would just have a negative in front, right?
Yeah. Oh, not negative. It would be -1 plus.
Oh
Do you
yeah,
think you
because
could
that's when you do.
elaborate on how that works real quick? I'm a little lost on that.
Yeah, that's when you do.
Just put your J omega as 0 and you would be just left with the real values, right? You have a +10 and +20 in the numerator and they're under multiplication. So 10 times 20 is 200 and in the denominator you have a -5 and +40. So that would give you a -200. So 200 by -200, that results in -1.
Yeah, but then how do you apply that to like the equation where we have the square root of omega squared plus our constant?
Yeah, in the square root equation, you just like you just add your DC gain to the equation. That's it. It's plus DC gain. In this case, it's a -1, so it's this entire equation -1. Ryan, could you just put a -1 after your
Thank you.
Yep. Yeah. And when you take the log of this, because it's a -1, you would just end up with a 0, right?
Wouldn't it be a complex number? I think it would be a complex number. Yeah,
It would be a
would.
complex number.
Yeah, logs and negatives gets weird. This would not be an example we would use. This gets beyond the scope of the class, but
Yeah.
yeah, your magnitude would become complex, which gets wonky. Don't worry about that. But yeah, when you write this out as in your gain equation, you would have your you would have a 20 log base 10 of -1 term, and this would become complex. So it would get funky. Don't worry too much about that. It's beyond the scope of the class. We're not going to ask you that, obviously, but just so you kind of have it in the back of your head.
In general, it's just like a rule, add the DC gain to the magnitude equation.
Yeah.
Yeah.
Yeah. Thank you guys so much.
I was just wondering, when you're doing the tan inverse of omega over -5, instead of like subtracting that value, could you just because it's -5, right? So couldn't you just add tan inverse of omega over 5 instead?
I believe that would give you the same answer. Let me double check. I believe tangent is symmetrical like that.
You just take the -5 out of the equation, right?
Yeah, it's symmetrical, so you could make it a plus tangent, inverse tangent of omega over 5. It would be the same.
Okay, thank you.
Yep. Cool.
And yes, the confusion that I created with problem set 2, capacitor voltage equation derivation, it's in module 3. Please check out the video or look at the notes for more clarification on that.
Yeah. We just forgot the 1 over S term with the DC.
Hey, I messed up pretty bad, man.
But yes, that full derivation is in the module 3 notes as well. All right, any other questions, general stuff, overview stuff, any topic?
Would you recommend that I fully understand that derivation of the capacitance equation that we were attempting to do in for the test? Like, is that worth spending time?
I would recommend understanding it. You should
Oh,
understand
bet.
everything, hopefully.
Oh, I do. You know me.
Okay, perfect.
I'm just kidding.
stopping the recording now.
Cool.